All right, we're going to get back into our study of the classical groups, and we're going to get right into it. We're going to begin with reminding ourselves about the general linear group over a vector space V, where our vector space, I always like to do this box. We name it V, it's got some arbitrary basis, it's n dimensions, and it's over some field F. And the general linear group is going to be, you're a member of that group, A, if you're a map from the vector space to the vector space, and it's an invertible map, right? So A and A inverse are both in the general linear group. Now, the way Gilmore presents this is slightly different kind of terminology. He talks about the general linear group as this group of all basis transformations inside a vector space, V. But in a lot of other books or documents you read are going to describe it as the set of all linear transformations between vectors in the vector space, or invertible, but the key being invertible. This is all equivalent, right? Because for every transformation from V to V, you can do the inverse transformation on the basis vectors and you'll get the same ultimate effect, right? So this is the same definition. So if you see it, they're presented different ways, you're just thinking forwards or backwards. And in fact, if we were to write this in our notation, we'd probably say A takes a basis E mu to a basis E hat mu, and A inverse takes the vector V to another vector V, if we were to kind of work that same reasoning. Just don't let that confuse us too much, right? But it is true. One thing that is true is this form here is all the very abstract description, right? We're abstractly defining the vector space and abstractly defining all of the linear transformations. What we want to get to quickly is the matrix interpretation of this. So what we have to do is we have to take this abstract group, and sometimes papers create a map called mu that takes us to the general linear group in n dimensions on the field F, right? So these vector spaces, by their definition, they already come with some field. Every vector space has some field as part of its definition. So we're not adding anything new here, but what we're doing is we're creating a representation of this abstract group, and that representation is in the form of n by n matrices. So this is a set of n by n matrices, and it's invertible matrices. So the set of all invertible matrices represent all of these linear transformations. And you have to believe that this is an isomorphism, that meaning that if I have two elements of the abstract general linear group, then I know that the matrix representation of A after B is going to be the matrix multiplication of the representation of A times the matrix multiplication of the representation of B. And we also need to know that the matrix multiplication of A inverse after A has to equal the matrix representation of A after A inverse, which has to equal the matrix representation of the abstract identity transformation, but more importantly, that has to equal the actual identity matrix, right? This guy here has to be all these ones down the diagonal, because we know that is the unit or the identity matrix in the matrix group. So it has to represent the same identity matrix. This has to be true. It has to represent the same identity matrix as in the abstract group. And then all these things make it essentially an isomorphism. So we can comfortably talk about this matrix group, and we're capturing everything in this abstract group. So that is the general linear group, and that is where we start. Every one of our classical groups is going to be some subgroup of this thing. And when we think of our classical groups, we're thinking of our classical matrix groups. It's going to be some subgroup of the general linear group. And the first one, we already discussed this in earlier lectures, so we're now going back and reviewing. But the first subgroup we're interested in is the special linear group. And the special linear group are all members of, first of all, they're all members of the general linear group in n dimensions over a field F, right? Such that the determinant of that matrix equals 1. And the idea here, and the reason when we brought this up in our previous discussion of this is these guys are what we call volume preserving. And we remember what that means is that the completely antisymmetric subspace of this, of the overall tensor product space, E1, E2, wedge, E3, wedge, dot, 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 wedge, En, where n is the number of dimensions of the vector space. This is called the volume element, this wedge product. And when that transforms under a basis transformation, say A, then we're looking for, we basically, what we're doing there is, hold on, when we do this, we're looking now to transform the basis. We want AE1 wedge, AE2 dot, 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 wedge, AEN. And that would represent this volume element under the transformation E hat equals AE, right? And we know from our previous work in the what is a tensor series, we know that this is going to actually equal a single number, the determinant of A, times E1 hat, E2, not hat, wedge, dot, 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 wedge, En. Meaning if you execute this basis transformation on the, you take the volume element, you execute the basis transformation, that is equivalent to just multiplying the volume element by a number, right? And that result is actually the same volume element in the hatted basis, right? And so we're interested in when the determinant is 1, the volume element in the hatted basis is exactly the same as the volume element in the unhatted basis. And we call that volume preserving. So we're interested in all those matrices that have a determinant equal to 1. And so it's easy enough. Okay, you just go to the general linear group, look at all the matrices that have determinant equal to 1, and pull them out. But the question is, that would be the special linear set. We're interested in the special linear group. So how do we know that if we do that process, we get a group? And of course, this is one of the easier things to show in this business. The determinant of a matrix A multiplied by a matrix B is the determinant of a matrix A times the determinant of the matrix B. So if A is an element of the special linear group and B is an element of the special linear group, we know that this determinant will equal 1, that determinant will equal 1, which means the determinant of the product will equal 1, which means matrix multiplication inside the special linear group produces another member of the special linear group. So it's closed. And we know that the determinant of the inverse is equal to is also going to be equal to 1 because we'll have this rule, the determinant of A inverse times A. Well, we know that that equals the determinant of I, which is equal to 1, right? So therefore, we know that the determinant of A inverse equals the determinant of A, which equals 1. We know this guy is 1, so we know that guy's 1. So the inverse is also a member of the group, and the identity is a member of it, of the special linear group, so it's a group. The point is it's a group. So that's our first important subgroup. And we always designate, so that's now the special linear group in n dimensions over the field. And it is a subset or a subgroup of the general linear group in n dimensions over the field. And that's our first of sort of our subgroups of the general linear group that's of note. And usually you'll notice the notation here, we just put an S, we replace this G by an S. And in all of our classical groups, when you see, in most of our classical groups, when you see a leading S, that means you're dealing with now a subgroup of this guy, right? A subgroup of the special linear group, which is therefore automatically a subgroup of the general linear group. That's not always true, though, because we're going to have things called the symplectic group, right? And there's an S there that's not implying you're a subset of the special linear group necessarily. Okay, so that's our first subset of the general linear group that's important. It's the volume-preserving groups, and that's the set, all of the matrices that have determinant 1. So if you're ever wondering why in all of this work determinant equal 1 was interesting, well, it's interesting because it's volume preserving. All right, so now that we've reviewed volume preserving groups, the next big one where we'll spend most of our time is these guys, the isometry groups, or as Gilmore calls them, the metric preserving groups. Same thing. Isometry groups and metric preserving groups are the same thing. Now these two groups only apply to vector spaces, right? Let's see, I usually do it the other way around. I say there's some basis, some dimension, and some field. But you have to have a bilinear form. Or, I'm sorry, you have to have a metric, right? You have to have a metric, which is some kind of form, right? Bilinear or sesquilinear, but it's a metric. And isometry groups, once you have a metric, you can define all of the interesting subgroups that preserve the metric. So what does that mean? Well, first of all, again, everything in these groups is always going to be a subset of the general linear group in n dimensions of the field, right? So there's definitely, we're drawing from this set. So what we're interested in the abstract form, let's do this in the abstract form too, right? Because these two groups, right, are isomorphic. So I can talk about these guys or these guys. Sometimes the language is easier here. Sometimes it's a little easier here. Let's start with thinking of this way. But my vector space has this inner product. So say I pull out an element A, right? I pull out A is going to be our transformation matrix. Well, what I'm interested in is if I take a vector V and a vector W, right? I want that inner product to equal AV AW. Meaning if I run the transformation on the two vectors, I don't want it to change the inner product, right? I want this inner product to be exactly the same. And you can think of this in terms of basis vectors, which is what you should always do by default. G mu E nu, right? That is defined to be this number, G mu nu, right? That has got to equal, and if we consider now, think of A in terms of, we think of A as a basis transformation, it's got to be, so we got to think of it this way, right? We have to thinking of A as a basis transformation. If I take two basis vectors and put them in the inner product, I get this number, which is that metric, right? Which is the metric of this. And then if I execute, the point is this equality has to be true for us to have, for A to be a member of the isometry group or the metric preserving group, this equality here has to be true. This number has to equal in the new basis, has to equal the metric element of the new basis, which is defined through this basis transformation where you sum over the k's and you end up with the mu nu downstairs and the mu nu, but this is now E hat, and you get G mu nu. This does not have to be true, right? For arbitrary matrix A, it's never going to be true, or rarely going to be true. But in those instances where it is true, A is of interest. It's a member of the isometry group. Now, we showed that the isometry group was actually a group in a previous lecture, but we'll do it again in a minute. But the point is we need to show that, the point is that this is a rare matrix inside the general linear group where this will be true, where this equality will be true. And when it is, it's a member of the isometry group. All right, so the question is all right, we've defined a member of what I was calling the metric preserving group by saying that it satisfies this rule, that the metric elements in the new basis is the same as the metric elements in the old basis. The metric elements don't change. However, it's easy to imagine pulling out all of the elements of the general linear group where that's true and say we did that, right? Say we had a set of all these elements A, be in this isometry collection. We'll call it an isometry collection. Is the isometry collection a group? Meaning, if I take an element A out of the general linear group and do this and discover that this is true, and I take an element B and discover this is true, if I do the matrix multiplication of A and B, if I know A is in the group and I know B is in the group, do I know that AB is in the group? Because if it isn't, then it's not closed and it's not a group. Also, is it true that the inverse of A will also be in the group? So I have to show those things in order to show the fundamental point that it's a group, right? And we did that in a previous lecture. I'll just run through the argument quickly one more time. The problem with the proof, right, is I've stipulated the inner product, but when I get to this point, I really don't know what to do with these coefficients. Now, the rule with forms or metrics as presented in Gilmore is this guy will come out over here and this guy will come out over here. We know that, but this guy comes out over here with a complex conjugation for sesquilinear metrics. And I haven't decided if this is sesquilinear or if this is bilinear, right? We haven't made that stipulation. We just said it's an arbitrary metric. So let's think about that. All right, so this is the our form rule that the way constants are pulled out of our form. It's pulled out if it's on the right, it's pulled out to the left. If it's on the left, it's pulled out to the right. The question is whether or not we want to give it the complex conjugation, right? So for right now, let's not, right? Let's just not do it. But once we have this rule, then we end up with this picture, which I've actually done before. I think I did this in, maybe it was either the last lecture or the one just before that, right, where we define the new metric element. Well, I did it several lectures ago, but again, we did something similar in the last lecture in a different context. But here what we're going to say is that the metric elements in the new basis, which are defined, right, because this is going to equal E mu hat E nu hat, right? Where we choose nu and nu because these are dummy indices, right? So this is the basis transformation of the unhatted basis to the hatted basis, and this is the definition of that. So this is not, there's no profoundness in this statement, but notice that I'm using Gilmore's convention on how to do the indices here, right? So in the end, you're going to see the transpose come on the right instead of the left, like we did before, where we used a different linear algebra convention. So I'm using Gilmore's convention. So now the question is we know how these rules work, so we can pull out these constants. So I pull this guy out on the left, and I pull this guy out on the right, and then I redefine this as the old matrix elements, because that's the definition of that, right? The definition of GK alpha is, in fact, this right here. And ultimately, we look at that as the matrix representation of the metric, because remember, we can represent the metric as a matrix with all the understandings from the previous lecture, now is given by this rule, meaning in the hatted basis, the matrix representation is the transformation times G times the transpose of the transformation. And this came out the opposite way in our previous lecture, only because of the convention we used on the basis transformation. So don't get wrapped up around that. I like to switch the notations just for the purpose of showing how all these things appear in different books, and also just to keep the mind very nimble about it. It's very counter to how lectures are normally done, where one system is used throughout from beginning to end for consistency's sake. That's just not my thing. All right, but notice we've said nothing profound yet, right? All we've done is we've essentially run the definition of the hatted matrix elements in terms of the unhatted matrix elements and the basis transformation. We've literally just transformed the matrix representing this particular metric. We've done nothing significant. And keeping in mind, by the way, that we may at some time want to put a complex conjugate here, which would put a complex conjugate here, which would put a complex conjugate here. But the real magic happens when I make the following stipulation. When I say that this must equal G mu nu. That is when I'm saying that these matrix elements must equal the matrix elements. The matrix elements in the new basis must equal the matrix elements in the old basis. And when I assert that, now I'm adding extra content, because what I'm saying is this matrix A that does all this work has to preserve these numbers. And when it does, then we know that A is a member of the isometry group. So let's assume that that's true, right? Assume that that is correct. If we assume it's correct, then we are saying we've selected A to be a member of the isometry group. Now we take another element of the isometry group, B, and we assume that this whole argument is true for B also. What we need to show is that A times B, the matrix multiplication of A and B, is also in the isometry group. In other words, we need to show that the isometry group is closed, which is sort of redundant. What I should say is the set of isometry elements is closed under matrix multiplication, and therefore it's eligible to be a group if it has all the other properties. So now if we jump to this notation here, we can actually move a little bit faster. For example, we can say that another basis transformation under B, which is also a member of the isometry group, right, is BG hat B transpose, right? The same process, because all this stuff applies to B just like it did to A. And then I can take G hat and I can substitute in its little transpose, its little definition here, right, through G. Oops. I need to get rid of that hat, right? Because I'm substituting for G hat. So I just have A, G, A transpose. Let me make that transpose a little better. And then because everything is associative, again, here's where associativity is a big deal, right? I end up with B, A, G, A transpose, B transpose, which we know how transposes work from linear algebra. It's B alpha G, B A transpose, right? So I know that I can find a new matrix, BA, which will go right from G to G double hat. But I know that we're assuming that B and A are members of this isometry set. So we know that this here must equal, so if I now say G hat, what was I using? Mu nu. G hat mu nu must equal G double hat mu nu must equal G hat mu nu, but we know G hat mu nu equals G mu nu, and therefore BA is a member of the isometry group. So if B is part of the isometry group and A is part of the isometry group, then the matrix B times A is part of the isometry group. Now, because we know that it all comes from the general linear group, now the question we have is about inverse, and there being a unique inverse. All right, so to talk about the inverse, let's start with the same argument, just setting it up. We're setting up for the inverse, right? We know that the k-elf matrix element in the transformed basis equals the k-elf matrix element in the untransformed basis. This is only true if A is a member of this special isometry group that makes it true, where this here, the value of that thing there actually equals EI, E, or E, not I, E, K, E, L, right? That is a statement of of what it means for A to B in the isometry group, right? And where these two things here are literally these two things here. And then we just do what we did before. We extract the LJ, we extract the KI, and we end up with this expression here where we've replaced that with its definition. All right, so now we assume that A is in the isometry group. Now we know that A has an inverse because A is a member of the general linear group. So we know it has an inverse. So call that inverse B. And I'm using the exact thing, the exact method Gilmore uses. This is his exact notation. So call the inverse B. So we just continue with almost the exact same argument we did before. I'm now going to take the matrix element in the hatted basis, and B we assume is the inverse of A. We don't know if B is a member of the isometry group though, but we know that B is the inverse of A. So B acting on this KL hatted matrix element is the same as BL acting on the unhatted matrix element, because we've already know that this equals this, right? Because we've assumed that A is already part of this isometry set. So because A is a part of the isometry set, we know that B acting on the hatted element is the same as B acting on this unhatted element. And so now we substitute this hatted element, right, here, this way, right? And because we know that this basically equals this, right? This is the KL element, this is the IJ element. But again, A doesn't change these things, so it really, it's immaterial. Once we do that, we're doing the same logic we did before. This becomes matrix multiplication over L, so that's the jth element of a matrix BA. And this is K sums out and you get IR, but it's over the wrong sort of index, so you find its transpose. So it's RI, and you end up with BA transpose, right? It's the product of transposes is the transpose of the product, right? And you end up with this operation. But you know by assumption that B is the inverse of A. So you know that this is the identity, this here is the identity matrix, and this is the identity matrix. And so you end up with this whole thing equaling this ends up being delta Sj, Gij, delta Ri, which equals SR, right? Which is what this here is G hat SR, right? When that's all finished. So GSR equals G hat SR, which is by the definition of an isometry. So we know that the inverse B does not affect taking the inverse element of A. If A is a member of the isometry group, we take its inverse, and we use the inverse as a transformation matrix on the metric, then that inverse leaves the metric elements invariant, which means the inverse is also an isometry, which means the inverse is in the isometry set. So now we know that the isometry set is closed and it has an inverse. And we certainly know that the identity element is a member of the isometry set, right? The identity element isn't going to change the matrix element. So the isometry set is a group. Now I'll let you work for yourself that this is also true for sesquilinear transformations. Nothing changes here for sesquilinear transformations. These guys end up with a complex conjugation on it, and that doesn't affect the argument. Okay, so what we have shown is that we have now shown that the isometries groups, the set of isometry elements are in fact groups, right? The effective isometry elements are groups. So we know that if we can now, given a certain metric, right? So what does this all depend on? This now all depends on this metric here. We have to once we are given a metric, we now have to find isometries of that metric. And that's sort of where the problem now stands. We must find isometries of a given metric, because we started with this idea. We are given a vector space with a metric. We now know that the general linear group will represent all basis transformations inside the metric space. We know the special linear group will represent all the volume preserving basis transformations for that vector space. Now we know that given this metric, there's some collection of elements of the general linear group that may keep that metric invariant. But we have to know, but all we know is that if there is such a thing, then that set of all the members of the general linear group that keep this metric elements invariant, meaning all the set of all different basis transformations that don't affect the matrix elements of the metric, we know that that collection of linear transformations, that collection of basis transformations is a group. So now the problem becomes characterizing metrics. For every different kind of metric we can come up with, we should be able to find an isometry group for it. We can't define isometry groups until we define all the different types of metrics we're interested in. And that's what we'll begin next time. We now will start characterizing the different kinds of metrics and looking for the isometry group of each of those metrics. And each time we find a metric that has an isometry group, we've now created a classical group. That's what the classical groups are. Classical groups are the isometry groups of very specific types of metrics, the metrics that we're interested in. And we'll begin that talk next time.